So I took a break at the end of part 4, and now this is moving on to number 5 in video part 2. But I hope you took the opportunity of taking a break and testing out your hearing here. And you can use the facility in there to test your mum and dad out as well and see if it's true about the highest frequency that you can hear going down as you get older. Now, next we're going to have a look at the vexed issue of transverse and longitudinal waves. And the reason I say it's vexed is that it's really hard to draw longitudinal waves. So what I suggest you do is that you stop and watch these two little clips. They're quite short. One's at 1 minute and the other's 8 seconds. And I think by the time you watch those, you will be able to tell me what the difference is between transverse and longitudinal waves. But I will attempt now to draw a picture that will show you. Here is something that's oscillating from side to side. Here it goes. Now, if it moves from left to right, then it goes, and that's a transverse wave. But what about something that was oscillating this way? When it moves from left to right, it's hard to draw. And it's this one, it is the longitudinal wave. So what we usually do is we imagine a slinky spring like the one you saw. And the slinky spring sort of goes, and then it goes, and then and then you see, I told you it was hard to draw. And this is meant to be an image that's a bit like, this one's transverse, this one's longitudinal. It's a terrible picture, that. But anyway, what's happening here is that the particles in the medium are going backwards and forwards this way, which is the same direction as the direction of travel of the wave. Whereas in the transverse wave, transverse sort of meaning across, and longitudinal meaning along. So it's kind of inherent in the meanings of the words transverse and longitudinal. But if we consider the longitudinal wave, then what happens is you get things that are called compressions. You get a compression where there are loads of particles, and then you get a rarefaction where there aren't very many particles. So this would be a compression, and then this would be a rarefaction, and then this would be a compression, and I told you it was a lousy picture. So R stands for rarefaction. Some people say, why isn't it called a decompression? C stands for compression. Compression means the medium is squashed up, so the pressure goes up, and a rarefaction means that the pressure goes down. In a compression, there are lots of particles, and in a rarefaction, there are fewer particles. But anyway, I think this is hard to draw. It's kind of easier to think about than it is to explain writing on a board. So I think if you're still struggling, I would encourage you to watch those two animations again, and then you should have it for nothing. And then finally, number 6. Number 6 is looking at solids versus liquids versus gases. The speed of sound is fastest in solids. The speed of sound is slowest in gases. And liquids, well, liquids are a bit slower than solids. And again, take time out to watch this short 2-minute video. It's an animation, it's rather charming, which suggests why this might be. In a solid, the particles are much closer together and they are attached to each other by very strong, rigid, stiff interatomic bonds. So if you push one end, then the message gets pushed along very quickly from atom to atom, from particle to particle. Whereas gases, typically in a gas, the particles are about 10 times further apart. And it's just by random collisions between particles that are totally independent of each other. There are no interatomic bonds. So In air, the speed of sound is 340 meters per second. In a solid, it typically might be 5,000 meters a second. You can look the data up. And that's all I've got time for today. Thanks for listening.